will join up their ideas. Well, here we have the definition of what a DOM space is. What is a DOM space? Well, if you have a vector bundle, then you have your base space and you have your total space. Well, if we consider the total space, then we can think of all the vectors that we have in that total space, and we can restrict our attention to the ones that are of length less than 1. Well, if we leave those untouched and collapse all the rest to only just 1 point, then we are creating the DOM space of that vector bundle. And that's what the definition is saying, that if we consider a subset of the total space A, which I denoted as A, well, consisting of vectors at least 1, this A is going to be collapsed. So that goes to only just 1 point, which I'll be denoting as, well, as infinity. And now we will use this DOM space construction to see what happens to the vector bundles on our DF structures and so on. Well, this doesn't seem quite straightforward at the beginning, because if we think just about saying, well, vector bundles, and why do we get this suspension here? Well, that's what I want to explain now. So here we have our already quite repeated diagram of VR. Well, I don't need to write it down. So our VR and VLRs and so on, and well, all around I've written the different ways that we can write the bundles over the canonical bundles over these manifolds. So starting here, if we think of our BLR+1 manifold, that you can remember is the Grassmannian of R+1 planes embedded in infinity. Well, then we have our canonical bundle, the universal bundle, gamma R+1. And what happens if I pull back this along this map? Well, that over here I must get the pullback bundle of this map and of this bundle. So we have this bundle over here. This corresponds to this. What happens over here? Well, using a pullback over this map, J sub R, we have this pullback over this bundle. And over here, we can go around the diagram as it's commutative and see what pullbacks we can get. If we start with this one, we can pull this vector bundle back over this diagram and see that it's the pullback. Well, this pullback bundle. This is a pullback bundle of this one. And if we go on another direction, we have this bundle here. So going along this map, we can also pull it back. So, and they are the same. So now, as what we want is to derive this commutative diagram of DOM spaces from this one, we have to think what we are doing to the vector bundles. So let's see. Well, to start with, when we write TVLR, we are just writing the same as the DOM space of the canonical bundle. Okay? And what? Is we are also dealing with these VRs. This is going to just be the DOM space of this pullback bundle. Okay, so this here is just notation. very important. And well, that is notation. And now we're going to derive the bottom part. So we have our first part here. Well, first what I'm going to see is what happens if I find the down space of this spectral bundle. So, this is a trivial line bundle, and well, what happens if we take the down space of a trivial line bundle? Well, that is it just produces the suspension of this. So going back to our notation here, the down space of that, we can only write. Sorry, I put one over here. This is too much. I think it's right now.
With the suspension.
Yeah, that's also true. Thank you. Yeah, that's right. And that's right. So, and the other one is just with suspension that I get over here. Well, that will be just the down space of that will be just CBL R plus 1. So we'll get from the bottom line of the diagram, we'll just get this that I've computed here. And the down space of the gamma R plus 1, that should be 0.1. So, just checking. It coincides with the bottom line over here. And of course the mat is also written as T this alpha. Now for the upper part of the diagram. So we have our we have and now if we find the down spaces of these two, of these, that should get the down space of all these. That's more or less the same as I did before. that's for the first bundle over there, and the second one is again only just taking the DOM space of that and following this mutation. I already get this. So now I can see that this explains that this diagram implies that our diagram wants to take the DOM spaces of the vector bundles. So we are nearly there, because now we know that the suspension map always induces that map between homotopies. And we also have that, well, from our diagram, we have that map over there. So, well, we have a map from homotopy patch of the. If we go to this map here, we have the map in this the diagram induces a map in homotopy. So we have that map, and then we only just have to compare some maps and let this go to infinity, so that we achieve a stable homotopy group. And with this stable homotopy group, what the DOM cobordism theorem says is that that is isomorphic to the n-dimensional equivalence classes or groups of n-dimensional manifolds. So that's the statement of the theorem. And well, at first, after going on, I think it is Algebraic.